Hey, what's going on, guys? In this video we are going to talk about minterms and maxterms, and also we are going to talk about Demorgan's theorem. Now before we go for the minterms and maxterms, now let's try to prove this one. Here we have a plus b times a plus b bar is equal to a. Now let's try to prove this one. In order to prove this one, we have to do the foiling method. We have to FOIL this one like this. We have to multiply. So when we multiply, that's AND. Okay, so this is going to become what? A times a. When we have AND, and if we have two terms like x or a, the final value is going to depend on whatever value a is. If a is 0, we are going to have 0, because 0 and 0, that's going to be 0. If a is 1, 1 and 1, that's going to give us 1. So it depends on a, so we will get a. And the next one is going to be a times b bar, so we will get a b bar. And the next one is going to be b times a, that's going to be ab. And the next one is going to be b times b bar. But b times b bar, b and b bar, when we have AND with the complement like b and its complement, it means it's going to be 0, because if one of them is 1, other one is going to be 0. And if this is 0, other one is going to be 1. In AND, if we have 1 0, it means the whole thing is 0. So this is going to be 0 right here. Finally, we end up with this one. Here you can see we can take a common. If we take a common, this is going to be 1 plus b bar plus b. So here we can see 1 is here, and whenever we have an OR gate, and if we have 1 1, it means the whole thing is going to be 1. It doesn't matter whether we have 0 or 1 right here. If we have 1 1, it means the whole thing is going to be 1. So we are going to have a times 1. So this is finally resulted in a. That's what we have to prove, right? This is equal to a. So we proved that one right here. Now when we talk about minterms and maxterms, there are two things. We have sum of product and product of sums. Now let's see what is product of sums. Sum mean OR gate. We are adding something, right? So x bar plus y. Let's look at an example for product of sums. So here we have x bar plus y, and also we have x plus y plus z. And here you can see this is sum. We are adding, right? We have plus sign, that's an OR gate, that is sum. And this is also sum. And this one is product, because we are multiplying, right? This is product. And here you can see this is product of sums, because we are multiplying two sums. So that is product of sums. Now let's try to draw the circuit of this one. Here we have what? We have OR gate. Each of them are OR gate, right? Each of them are OR gate. So here we have two OR gate. And for the first OR gate, we have x complemented. Complemented mean we have NOT gate right here. So this is x. This is complemented mean we have added a NOT gate. And then we have a y going through this one. This is y. And for the next one, we have x, y, z. We have three input, x, y, z. And both of them are connected to the AND gate. That's what this expression means. So both of them are connected to the AND gate. So this is called product of sums. Product of sums. In short term, we call POS. Okay. Now let's see what is sum of product. So sum of product is, let's look at an example. Let's say we have f that is equal to xy plus x bar yz plus x bar c. Here you can see this is a product. This is also a product, because we are multiplying product. So when we have AND gate, that's product. And this is also product. And we are adding the products. So that's why we call this one, we are summing the products. So this is sum of products. Sum of products. So that's called, in short term, we call SOP. So this is product of sums, and this is sum of products. So that's the basic thing we have to know. Now let's look at a question which is asking us to express the final answer in terms of sum of products. Now let's look at the question. In order to do that, I have to get rid of this one first. Let's get rid of all of these things. Okay, let's continue this one right here. Let's say we have this question right here. G is equal to xy plus x bar plus z times y plus z bar, and the question is asking write this final answer as sum of products. Write this one as sum of products. Here you can see, here we have product of sum, these two are product of sum, then we have sum of product, so we have both of them together, but the question is asking for sum of, express this one as sum of product. Now let's see how we can do that. So in order to do this one, first we have to FOIL it. That's the first step. When we have a question like this, the first thing is FOIL it. So FOIL means we multiply these terms and simplify. Okay, let's go ahead and continue. So xy remains the same, and if we FOIL this one, this is going to be what? X bar y, and this is going to be x bar y plus x bar z bar plus yz plus z bar. Z bar is going to be 0 because when we have an AND gate and we have complement, like if z is 1, this is going to be 0. If z is 0, this is going to be 1. So we have 1 0. When we have an AND gate and we have a 0 right there, it means the whole thing is 0. So this is going to be 0. Now we are left with this one. Now what we can do with this one, here you can see this one. For the first one, we can take y common. If we take y common, this is going to be what? X plus x bar. X plus x bar, when we have an OR gate and we have x and its complement, it means one of them is going to be 1. Because if this is 1, this is going to be 0. If this is 0, this is going to be 1. So there is 1. When we have an OR gate and if we have a 1, it means the whole thing is going to be 1, right? So this is going to be 1. And let's look at the next one. So we can replace this one with 1. And this is, we took these two terms, we are left with this one. Let's copy this one down right here. X bar z bar plus yz. So we are left with y plus x bar z bar plus yz. Okay, let's see whether we can simplify this one furthermore. Here we can do one more thing. If you take y common, this is going to be 1 plus, here we have a z, and we are left with this x bar z bar remains. And again we have a OR gate with 1. If we have 1 1 in OR gate, the whole thing is 1. So instead of writing 1 plus z, we can replace that one with 1. So this is going to be just y, right? Because y multiplied by 1, that's going to be just y. Then we are left with y plus x bar z bar. So finally we brought our term in terms of sum of products. This is sum of products because we are summing a product like this, right? So this is sum of product. And if they asked us to write this one in terms of product of sums, we can use another thing. There's a rule says that a plus bc is equal to a plus b times a plus c. Here we have what? Here we have y plus x bar z bar. This is our finally derived answer, that is sum of product. Now we want to express this one in terms of product of sum. Product of sum should be looking like this, right? So we can expand this one similar to this. So if we expand this one, what's going to happen? Here you can see the pattern. A plus bc, that's going to be a plus b, the first term, and the second term, right? So this is also going to be same. This is going to be y plus x bar times y plus z bar. So this is going to be the product of sum of this final expression. Okay, now that's it for the Minterms and Maxterms, and let's talk about Demorgan's theorem, because similar to this one, there are two different equations which we can use for simplifying these kind of things. That is in Demorgan's theorem. There are two things. Let's look at that one. Okay, let's get rid of this. Demorgan theorem says that if we have a plus b whole bar, that is equivalent to a bar plus, or we can say a naught and b naught, right? So this is equal to this one. In some book you will see it will be expressed like this: a plus b, instead of bar they will put something like these primes kind of stuff. This is same, right? And also the Demorgan's theorem says another thing, like if we have a and dot mean and b whole bar, that is equal to a bar plus b bar. So this is, in other words, we can say a naught plus b naught. And in some books you will see it expressed like this, ab prime. Okay, now let's look at this one individually. Let's look at what is the first term represents. Now let's look at that one. Let's copy that one down right here. First we are going to see what is a plus b whole bar is equal to a bar b bar mean. So when we have an OR gate, first one is OR gate, right? OR gate, and that is connected with a input and b input. Finally we have a NOT connected, like NOT gate connected to it. That is what this expression represents. So this is what it means. And Demorgan's theorem says this one is equal to this one, that is equivalent to a bar plus b bar. A bar, not b plus, multiply, right? Multiply mean AND gate. So AND gate, and a bar mean a NOT. So NOT gate connected, and here we have the a is connected with NOT gate and b also connected with NOT gate, and that is equivalent to this expression. Okay, and in other words, instead of putting NOT gate at the end, we can also express this one like this. OR gate, at the end we put something like this, a NOT like this, and we connect with a b, right? This is called NOR gate. So when we have a NOT at the end of this OR gate, that is called NOR gate. And here also we can do the same thing. Instead of this NOT gate, we can connect a NOT. It's the same thing. So it's not different, it's the same thing. Like NOT gate, we can do the same thing. If we connect a NOT, that's mean NOT. So let's look at the truth table for NOR gate. NOR gate truth table is exactly opposite to the OR gate. In OR gate, you know that when we have a, b, and when we talk about two terms, we have 2 power 2, four different orientation. We can have 0, 0, we can have 0, 1, we can have 1, 0, and 1, 1. Right? Let's look at the truth table for NOR gate. A, NOR, B. In OR gate, if we have 0, 0, that's equal to 0. But in NOR gate, that's exactly opposite. Think like OR gate complemented. So 0, 0 mean in OR gate, it's 0. So if we complement 0, what's going to happen? We are going to get 1. And in OR gate, if you have 1, 1, it's going to be 1. But in NOR gate, that's going to be 0. And here this is going to be 0, this is going to be 0. So NOR gate is exactly opposite to the OR gate. Okay. Now let's see some application. Like when we have a NOT gate, can we replace this? Instead of NOT gate, can we use a NOR gate? We can use it. If we tie the nodes together, if we tie two of these input together like this, that's going to be equivalent to a NOT gate. You will see. For example, if I put a 0 right here, what's going to happen? It's going to split into 2. We are going to have 0, 0. Finally, what's going to be the output? We will get a 1, right? So 1 is going to be the output. When we have 0, 0, 1 is output. And NOT do the same thing. In NOT, if we put a 0, this is going to result in 1 because NOT is complement. And for NOR gate, if you put a 1 right here, let's see what's going to happen. If we put a 1, that's going to split it like this. 1, 1. 1, 1 is what? 0. In NOT gate, if you put a 1 right here, you will get a 0. So it's going to behave same like NOT gate if you tie these two input together. So instead of NOT gate, we can replace this one with NOR gate. Tie these two input together and connect it like this. Okay. So this is the first rule of Demorgan's theorem. Now let's look at the second equation of the Demorgan's theorem. So let's get rid of this one. Okay, so the second equation says that a dot b whole bar is equal to a bar plus b bar. Now let's see what is that is. A dot b whole bar mean what? A dot b mean this is AND gate, right? AND gate, and at the end we have complemented. So we have two input A and B, and at the end we have complemented these two. So this is connected to the NOT gate, and Demorgan's theorem says this one is equal to A bar plus B bar. A bar mean what? A connected to the NOT gate, and B bar is B connected to the NOT gate, and both of them are connected to NOR gate. That's what I mean, OR gate, because plus, right? So both of them are connected to OR gate. So that is what this expression means. And also we can do the same thing like we did before. Instead of this NOT gate, we can replace that one with a NOT right here. So AND gate connected with NOT, and here we have A, B. So this is we call NAND gate. NAND gate. And that's going to be equivalent to, similar to what we did before. Instead of this NOT gate, we can put a NOT at the beginning of this OR gate. It's the same thing. Okay. And here the input is A and B. So it means A and B are complemented and connected with OR gate. And that's it. So this is NAND gate. Now let's look at the truth table for NAND gate. If you look at the truth table for NAND gate, that is exactly opposite of AND gate. In AND gate, okay, let's look at the variables. We have 0, 0, 0, 1, 1, 0, 1, 1. In AND gate, if we have 1, 0, the whole thing is 0. So final results what we get, here we are looking at A, NAND, B. So when we have a 0 in AND gate, the whole thing is 0. The final answer is going to be 0. But in NAND gate, we have to think it as complement of AND. So if it's 0, we are going to get a 1. And for this one, we are going to get 0 in AND gate, because if we have 1, 0 in AND gate, that's 0. But in NAND gate, that's going to be complement, so we will get 1. For this one, we will get 1. But for this one, we will get a 0. So you can see this is exactly opposite of AND gate. So you have to think it like complement of AND gate. That's going to be the NAND gate. Now let's look at a circuit. Can we replace this NOT gate with the NAND gate? Can we do the same thing we did before for NOR gate? We can do the same thing. Like if you connect these two input together and put it like this, let's see what's going to happen. So this is NAND gate. Now if you put a 0, that's going to split around 0, 0. And 0, 0 results in what? We will get a 1. And if we put 1, gonna split around like this, and we will get what? 1, 1, that's 0. The same thing happens to NOT gate. If you put 1, you will get a 0. If you put 0, you will get a 1. So NAND gate also exactly same as NOT gate if you connect these two input together. So instead of NOT gate, you can replace this one with the NAND gate when we tie these two input together. Okay, and that's it for this Demorgan's theorem. Now let's look at the application. Like let's say we have a circuit like this. Okay, let's say we have a circuit. Okay, let's draw the circuit first. Okay, here we have a circuit with AND gates, 3 AND gates connected to an OR gate. Okay, connected to an OR gate like this, and we have one input that connected to the NOT gate, and one direct input, and 2 input connected to NOT gate, and 3 input like this. Let's say this is XY. Let's call this one YZ, and let's call this one XYZ. Okay, and the question here is asking design using only NAND gates. Design this circuit using only NAND gates. Okay, now let's see how we can do this. First, it's easy to make this one a NAND gate, because if you put a NOT right here, this is going to be a NAND gate. But if you do that, you have to do the same thing right here, because if you put this one and this one right here, it means this one is going to be a NOT and this one also going to be a NOT. NOT cancels each other, so it's not going to change anything. It's going to give us the same results. So if you try NOT in two sides, you will get the same results. So this is not going to do anything, right? So now we have turned these three into NAND gates. So that's our question, NAND gates. But we have to change this one also into NAND gates, and also we can change this NOT gates into NAND gates as we seen before. Now let's go ahead and design the whole circuit. So first what I'm going to do is, for this one I have to use Demorgan's theorem. Demorgan's theorem says what? When we have OR gate, like the total OR gate, let's look at this expression first. So this one we seen before, a plus b bar, not this one, the second one. And the second one says a dot b bar, b whole bar, that means a connected here, b connected here, and NOT. This means this is connected to the NOT gate, we can put a NOT, that same thing. So this is NAND gate, that's equivalent to an OR gate with input of A and input of B complemented like this, right? So this is what happening right here. Instead of this one, we can replace that one with a NAND gate. This is actually a NAND gate, right? So we can do the same thing right here. If we replace with this one with this, that's going to be same thing. So that's what I'm going to do right here. Let's go ahead and draw the new circuit. For NOT gate, we can do the same thing like before we did. We can connect two input together and replace that one with a NAND gate. So that's going to give us a NOT gate. And this one remains the same, NAND gate. And then this is X, this is Y. And here we are going to do the same thing. We connect two of the input to the NAND gate, connect it like this. This is going to be Y, and here we do the same thing, connect it like this. This is the NAND gate, and the last one same thing, NAND gate connected to three inputs like this, X, Y, Z, and all of them are connected to the, here it's OR gate complemented at the beginning. So it means it's similar to, if you have complemented in the beginning, that's similar to a NAND gate. So we can replace that one with a NAND gate like this. So that's going to be the same thing, okay? And that's going to be the equivalent circuit for this one, designed using only NAND gates. Now we did that one right here, okay? And that's how we do this kind of things. I hope this helps. Thanks for watching.